Hello everyone, this is Unit 0, Lesson 1, Rate of Change. So in this unit, we're going to be discussing linear relations. And a linear relation is basically the relationship between an x and y value for a line on a graph. So this is following up some of what you would have learned in your grade 9 course and just kind of leading into where we'll be going in this grade 10 course. So we're going to start with an equation we have here. And we're going to create a table of values for this relation. So create a table of values and graph the relation y equals negative x plus 6. So what that means is I'm going to substitute in all these values for x in order to get my y value. So we're going to sub in x values. Okay, so my first x value I have on my table here is 0. So if I sub that into the equation, you should find that y is equal to 6. Okay, and hopefully we can see a pattern after we do a few of these. We substitute a 1 in, and we're going to substitute that 1 into brackets because there's a negative attached to that x. We should get 5. Okay, you can kind of see where we're going. We can just talk through the other points. So if we substituted 2 in for x, you're going to have a negative 2 plus 6, so that'll be 4. And hopefully we can see a pattern here that our y values are going down by 1 each time. Okay, so now we'll go ahead and we will graph this relation, remembering that we can look at our table of values as an ordered pair or as points. So for example, we could say that for 0, 6, that is an ordered pair that we would write like that. And our next ordered pair is 1, 5, 2, 4, and 3, 3. So we'll work to just first plot those points. So 0, 6, we're going to go over 0 and up 6. 4, 5, 6. And then our next one is over 1, 5, 2, 4, and 3, 3. Okay. We're going to connect those dots with a straight line. You should always use a ruler or straight edge. Okay, and looking at our graph now, hopefully we can all see that we have a straight line. So the equation and the format of the equation is a very particular type of equation of a line that we will talk about for the first half of this unit before moving into a different format for an equation of a line. But let's first talk about some of the characteristics of this equation. Okay, so one of the characteristics of the equation of a line is our rate of change, and this is also called our slope. So these two words are really used interchangeably. They mean the same thing. So the letter M is used to represent slope. It's from the French word monter. Okay, and that word means to climb. So remember, slope and rate of change are used the same. So slope is simply a measure of the steepness of a line. It indicates the rate of change in the y values as our x values increase. Okay, so if we were to look back at our table, I'm just going to erase this part here. Our rate of change is basically what is happening as our y values, or what is happening with our y values as our x values increase by 1. So you can see if you look here, my x values, as I go from 0 to 1, it's increasing by 1. As I go from 1 to 2, it's increasing by 1. And as I go from 2 to 3, it's increasing by 1 again. So what's happening to my y values when that's going on? Okay, well, as my x values increased by 1, my y values went from 6 to 5, so they're actually going down by 1. And then they go down by 1 again, and they go down by 1 again. And in order for it to be a line, they should be going down the same amount each time. Okay, and we'll talk about that means later. So really what we're looking at here is that our m represents our slope. And so we're just going to kind of write an equation for that. There's two equations we write. So if we're basically looking at what's the rate of change of our y values as the x values increase. So that's as we, in mathematics, we look at as division. So basically, what's the change in our y values divided by that increase of 1 in our x values. So we will sometimes say that it's the change in y over our change in x. So this is a Greek letter, delta, and it means change in. Okay, so the change in my y value over the change in my x value. You'll also sometimes see slope written as our rise over our run. Okay, and our rise is simply because it's our change in our y values, which our y values run vertically, so they run kind of rising or decreasing, and over our run is our x values, because our x values run left to right. So we'll take a look at some of the equations below so you can see what I mean. So let's first look at determine the rate of change for each line shown below. So if we look at A, for example, remember that m equals our rise or our change in our y value over our run, which is our change in our x value. Okay, so what I mean by that is, say I picked any points on my graph. Let's say I pick this point on A and this point on A. Okay, so my slope or my rate of change is saying, okay, how much am I rising as I move from left to right on this point? Okay, well, from this first point I circled in blue, I'm rising 1, 2, 3, 4. I'm going to say m is rising 4. It's my change in my y values, because my y values run vertically. And then my run is going 1, 2. So you can see, once again, I'm rising a positive 4, and then I'm running a positive 2. So we would write that as 4 over 2, and we'd always want to simplify it. Okay, and we could write it as 2 over 1 or as just 2. It's suggested that when we're trying to determine our slope for the purpose of graphing, leave it as a fraction. So it's easier to graph. And we'll see examples of this in later lessons. But if we look at B, so again, I'm going to pick 2 points and we're going to kind of evaluate them looking at it from left to right. So B and my M, looks like I'm going to rise. Well, this time I'm actually going down. So I'm going down 2 and I'm going over in a positive direction again, 3. So my slope is a negative 2 over 3. Okay, C and D are a little bit unique. C is a horizontal line, right? It runs perfectly flat or perfectly parallel to the x-axis. So we'll have to take a look at what does that mean for slope. So remembering that slope is rise over run. Well, if I look at, say, these 2 points, okay, well, how much do I rise to go from one point to the next? I don't rise at all, right? It doesn't rise, it just runs, right? So I rise 0, but then I run 2. So 0 divided by 2, my slope is just 0. And hopefully intuitively that makes a bit of sense, because if I have a completely flat line, as flat as the floor, there is no steepness to it, right? It has a steepness of 0. So that should logically make sense that the slope or the rate of change would be 0. And our last one, similar kind of reasoning. This time if I move from, let's say, this point to this point, my rise is going to be 2. Okay, but what's my run going to be? How much do I have to move left or right? And the answer to that is 0, right? It doesn't move left or right at all. Well, in math, we cannot divide something by 0. So if I have 2 divided by 0, my slope is actually what we call undefined. Right? They cannot measure the steepness of this. And again, hopefully this will make sense, because if you think about if we had a hill that was perfectly straight up and down, you couldn't climb it, right? There is no steepness to it because it's perpendicular to the ground. You can't physically climb that. So therefore the steepness is undefined or not possible. Okay? Okay, so we're going to determine the rate of change for each of these linear relations, keeping in mind that our rate of change is our rise over our run, and it's also, like we had said on that previous page, it's our change in our y values divided by our change in our x values, okay? So I'm just going to write here again, change in. Okay, so if we look at A and we see, okay, as my x increases by 1 unit, right, each of these are increasing by 1, what's happening to my y value? Well, as x goes from 0 to 1, my y value is going from 6 to 13. So that's increasing by 7. And we'll check to see if that's happening the next time. So go from 13 to 20. Again, that is increasing by 7. And then from 20 to 27, it's again increasing by 7. So if I look at what's the change in my y value divided by the change in my x value, well, the change in my y value as I go from 1 to the next is 7, and the change in my x value is 1. So we could write it as 7 over 1, or just 7. All right, let's take a look at that next example. So this time my x values are going up by 2. So we'll still look at it. Remember, it's what's the increase in y as my x values increase by 1, but we could always get it down x to 1 by just dividing. So for now, our x values looks like they go up by 2 each time. So what's happening is my x values go up by 2 to my y values. Well, my y value goes from 11 to 3, so it's going down. How much is it going down by? 11 to 3, it's going down by 8. And then it goes from 3 to negative 5. So again, that's going down by 8. And then negative 5 to negative 13 is going down by 8 yet again. So this time, my y values are decreasing by 8 as my x values are increasing by 2. So just like with any other fraction, we're going to want to simplify that. So a negative 8 over 2 is going to reduce to a negative 4 over 1, or just 4. Okay, take a minute to pause this video and see if you can work through the rate of change for that last example. Okay, so there's your rate of change, or your slope for that third example. Y is increasing by 5 as x is increasing by 3. We're going to look at some graphs with some real life applications and see if we can determine, again, the rate of change, as well as putting on the units for that, keeping in mind that rate of change is our y over our x. So we're going to have to consider what is our y unit in this case, what is our x unit in this case. We have money in a bank account here, and we have a couple of variables in play. We have the number of weeks, that's our x variable, and we have our account balance in our y variable. So it looks like how much money is in our account depends on the number of weeks. So when we are looking at our rate of change, we're going to be looking at how much money is basically being deposited or taken out of a bank account per week. Okay, so let's pick a couple points to have a look at. Let's say, because we want to pick some points that fall nicely on the crosshairs so they're not hard to kind of interpret. So that one looks like it does. And this one looks like it does too. And those look like easy values to kind of deal with. So let's establish what's our rate of change, or what's our rise over our run. So this one goes, and this is a little different because in this graph we have a scale to consider, right? Each line is not worth 1 unit anymore. Each, it looks like every 1, 2, 3 line is worth about 50 units. So as I go from this first point in blue and I go down, it looks like I go down to what is 100 along my y-axis, right? So I go from 150 down to 100. So I'm just going to put on there on my graph so I can see I went down 50. And then I go over, and again, it looks like if I look on my x-axis how much I'm moving over from 2 to 4. So the scale is not 1 to 1 on those blocks.
So 2 to 4 means I'm moving to the right by 2. So my rise in this case was a negative 50, and my run was 2. So again, we can simplify that. So it looks like negative 25 over 1. So if we were trying to determine the amount of money in this bank account, we could say that it's going to be a negative $25 per 1 week. Okay, because that top number represents money and that bottom number represents the number of weeks. So negative $25. And that makes sense because it looks like the bank account, the amount in the bank account is going down. So it should be money coming out. It should be a negative amount. Okay, let's take a look at this next example. So now we have the height of a small plane, and we're looking at the height, okay, over the time. So meters per minute in this case. So if we take a couple points here, let's take this point. Looks like it falls on a nice number, and we'll take this last point here. Okay, so my rise looks like I'm starting at, this is about 1500. So we'll just highlight where we started, right? That point starts at 1500 and it goes down to there. So it's going down 1500 down to 1200. So it's decreasing by 300. And then it's going to run from 2 to 4 again. So it goes from 2 all the way over to 4, which showing it has a run of 2 as well. So our rise is going to be a negative 300 and our run is going to be 2. So again, we can simplify that to a negative 150 over 1. So if we wanted to quantify that with our units, we would say a negative 150 meters, because that's our top number, our y value, per 1 minute. All right, in this next example, we're going to try to determine the rate of change when we're given coordinate pairs. So when we're actually given the coordinates on the graph, we're going to see if we can come up with what's a formula that will always work, so we don't have to actually put it on the graph. So if we look at this graph, just knowing what we know from graphs, we have to determine what's our rise and what's our run. Okay, well our rise, we went from 5 to 8, so it looks like we have a rise of 3, and our run looks like it went from 3 to 9, which means we have a run of 6. So think about what we did here. We didn't have any grid lines. We just had to go by our coordinates. So how did we determine that we had a rise of 3? What did we do with those y values to determine that? Well, we used our 8 and our 5. So we basically were finding out the difference of those. We did the same thing with our run value, right? We found that our run was 6. And we determined that by looking at the difference between those x values. So we did 9 minus 3 to determine our run of 6. So now if we wanted to put that into our slope, we would do our rise over our run, which is 3 over 6, or we would reduce it to 1/2. Okay. So how could we simplify this into a formula? What did we do to figure out our rise? Well, we subtracted our two y values from each other. So we basically took that y2 and subtracted y1. And then we did the same with our x values. We took x2 and we subtracted x1. So our slope formula, if we were given coordinate pairs, would be y2 minus y1 divided by x2 minus x1. So now that we're not always going to use a graph, if we're just given points on a graph, we should be able to find our slope. We should be able to find our rate of change. We'll try an example together, and then you can pause the video and try the other one on your own. Find the slope between 1, 3 and 5, 2. Just like they identified in this graph here, if we label our coordinate pairs as x1, y1, x2, y2, then it's easier to then plug into the formula. So we're going to call this first point here point 1. So I'm going to label it that this is x1 and y1. And then I will label our other point as point 2, so we'll call x2 and y2. So the formula we just came up with was that slope is y2 minus y1 divided by x2 minus x1. So let's plug in to those variables with those numbers from the points. So y2 is going to be 2 and y1 is 3. Our x2 value is 5 and our x1 value is 1. So if we simplify, 2 minus 3 is a negative 1 and 5 minus 1 is 4. So that's our slope of a line those 2 points pass through. Let's label the points with our x1, y1, and then pause the video and see if you can calculate the slope. Okay, so again, that first point will be point 1, so we'll call it x1, y1, and then that second point will be x2, y2. Pause the video and see if you can determine the slope. So when you plug in the points into the slope formula, you should get a negative 4/10, which remember you always have to reduce your fraction to lowest term, so that should reduce to a negative 2/5. That's it for the note for today.